In this video, we will learn about oxidation numbers, what they are, how to calculate them, and how to use them to identify redox reactions. Electrons in chemistry can be quite hard to keep track of. We have a good understanding of ionic bonding, where anions and cations attract one another. And we have an understanding of covalent bonding, where shared electrons sit between atoms, bonding them together. However, it's common for complex ions to also contain covalent bonds. For example, the nitrate anion. And it's also common that the types of bonding can change because of a reaction. It's easy enough keeping track of electrons when we're dealing with purely ionic or purely covalent bonding, but what if we have a mixture? It would help to have a simple system that will keep track of electrons in all circumstances. This is a carbon atom. A carbon atom can react with an oxygen atom to produce a molecule of carbon monoxide. This is clearly an oxidation reaction, since we're adding oxygen to the carbon. And carbon monoxide can undergo a further oxidation to form carbon dioxide. But what's not clear from this is which atoms have more electrons than normal and which have fewer. For this, chemists invented an accounting system that works for covalent bonding and ionic bonding. This system relies on the effective position of electrons in covalent bonds. If the electrons are closer to one atom than another, the atom they're closest to is considered reduced, and the atom they're further from is considered oxidized. We can remember this relationship using the mnemonic oil rig. Oxidation is the loss of electrons, and reduction is the gain of electrons. If the electrons in a covalent bond are closer to one atom, we can consider that atom to have gained electrons, and therefore be reduced. We can use the electronegativities of the atoms of the elements in a covalent bond to predict which atom electrons will probably be closest to. The electronegativity of carbon is much lower than the electronegativity of oxygen. This means we'd expect the electrons in carbon-oxygen bonds, for instance in carbon monoxide and carbon dioxide, to be closer to the oxygen atoms. In this accounting system that chemists came up with, we imagine that the atom the electrons are closest to actually gains those electrons. So instead of atoms, we imagine anions and cations. Using this method, we can identify that carbon in these reactions is going from a neutral atom to an effective 2+ ion to an effective 4+ ion. This system is not supposed to tell us what atoms or ions are like in reality. Instead, it helps us differentiate between different states of atoms or ions in different circumstances. The system that chemists came up with is the oxidation state of an atom or ion, which uses oxidation numbers. The term oxidation state is more commonly used when we're referring to the atom or ion itself, while the phrase oxidation number is more commonly used to refer to the actual value. However, they're often used interchangeably, and that's fine. An unbonded atom, like an atom of carbon in the gas state, is assigned the oxidation number 0. A simple anion is given the oxidation number equivalent to its charge. And we do the same for a simple cation. It's crucial to remember that an oxidation state is not identical to a charge. The charge of an atom or ion is its overall charge based on the relative number of electrons and protons, while oxidation state is part of an accounting system that assumes we're dealing with 100% ionic bonding. We write oxidation numbers with the sign on the left-hand side of the number, and we write charges with the sign on the right-hand side. Of course, there are plenty of situations where the oxidation number and the charge of an atom or ion are the same, but we need to distinguish between the two because they have different meanings. Now, let's have a look at the oxidation states of atoms or ions in different substances. The elemental forms of the elements can be solid, liquid or gas, and you can have different allotropes. An atom of an element, bonded or unbonded, is given the oxidation state of 0. If there's a covalent bond between atoms of the same element, we consider the atoms to be identical. There's no sensible reason we'd treat one atom as oxidized and the other as reduced. so we simply give both atoms the oxidation state of 0. The next easiest oxidation states to assign are those of simple ions. First, we examine the charge, identify the value, and then convert to the oxidation state by moving the sign to the opposite side. So a sodium ion has an oxidation state of +1, an aluminum ion has an oxidation state of +3, and a nitride ion has the oxidation state of -3. Now what if we're dealing with simple ionic compounds where the charges of the ions aren't given? We can use the same understanding we use when we figure out the formulas for ionic compounds, using the charges we expect for metals and nonmetals. A neutral ionic compound must have a net charge of 0. Oxidation numbers are based on the same principles of conservation of electrons, so the same applies. For a neutral compound, the sum of the oxidation numbers of the individual components must be 0. We can use our understanding of the common ions formed by sodium, magnesium and oxygen to figure out the other answers. Polyatomic ions, ions that contain more than one nucleus, can be more tricky. For instance, the nitrate anion, which has a net charge of 1-. Even though we've got a net charge, we can apply the same principle as we did with neutral compounds. The oxidation numbers of the components must sum to the equivalent value of the overall charge. The overall charge is 1-, so the oxidation numbers must sum to -1. On the left-hand side, we have the unknown oxidation number of nitrogen, and 3 lots of the unknown oxidation number for oxygen. Oxygen is more electronegative than nitrogen, so in a 100% ionic system, we'd predict that the oxygens in this system would have the bonding electrons. Oxygen typically forms 2- ions, so we can assign the oxygens an oxidation number of -2. If we evaluate our expression and rearrange, we end up with an oxidation number for nitrogen of +5. In equations, you may see oxidation numbers written as numbers or as Roman numerals above the element symbol. Just be careful not to go backwards. Just because we've assigned an oxidation number of +5 to this nitrogen does not mean in reality we're dealing with a nitrogen 5+ ion. Oxidation numbers allow us to compare atoms or ions in different circumstances. They don't necessarily reflect the charge of atoms or ions in reality. Let's do one more example, the permanganate ion. When a metal and a nonmetal react, we expect the nonmetal to form anions and the metal to form cations. So here we'd expect oxygen to be in the form of O2-. Again, we're dealing with an ion with an overall charge of 1-, so the sum of the oxidation numbers must be -1. With 4 oxygens, we have 4 lots of the -2 oxidation number. When we evaluate and rearrange, we end up with an oxidation number for the manganese of +7. Next up, polyatomic ions can form part of ionic compounds just like simple ions. For instance, calcium carbonate. The starting point is to know that the common ion for calcium is calcium 2+. So to balance, the charge of the carbonate ion must be 2-. Doing the simple ion is easy, and we can do the carbonate just like how we've done every other polyatomic ion. As before, we'll assume that oxygen has an oxidation number of -2. When we evaluate and rearrange, we end up with an oxidation number for the carbon of +4. Now that's all the easy categories for assigning oxidation numbers. Let's move on to the hard one. That's covalent substances like carbon, carbon monoxide and carbon dioxide. For pure carbon, the oxidation state is set at 0. But we have to figure out the oxidation numbers for carbon in carbon monoxide and carbon dioxide. To figure those out, we need to remember that the typical oxidation state of oxygen in a compound is -2. For carbon and carbon dioxide, the oxidation number is +2. Here we relied on the fact that the sum of the oxidation numbers is 0. When we do the same for carbon dioxide, we need to be careful to multiply the oxidation number of oxygen by 2. This gives us an oxidation number for the carbon of +4. But there's an unusual example, hydrogen peroxide. If the oxygen in hydrogen peroxide had the oxidation number of -2, then the hydrogens would have to have an oxidation number of +2. Hydrogen atoms only have one electron, so it doesn't make sense to talk about hydrogen in a +2 oxidation state, since that would be the equivalent of losing 2 electrons. So what's actually going on here? This is the structure of a hydrogen peroxide molecule. Oxygen is much more electronegative than hydrogen, so the electrons in the oxygen-hydrogen bonds end up closer to the oxygens. But the electrons in the oxygen-oxygen bond are exactly in the middle. If we try to turn this system 100% ionic, this oxygen-oxygen bond poses a problem. It's not reasonable to say that one atom loses electrons and one atom gains electrons, so in this case we keep the bond. What we end up with are H+ ions and O- ions. This is why we see oxygen with a -1 oxidation state when it's in a peroxide. This is a lot to remember. Thankfully, there's a system of rules that can help cut the answer. They can be easily remembered using 1,2,3 FHOC. The number 1 refers to group 1. In a compound, we assume group 1 metals will have an oxidation number of +1. Next, the group 2 metals, which we assign the oxidation number of +2. And we assign +3 to members of group 3. Remember that if a rule comes first in the sequence, that rule gets priority. The next rule is that fluorine in a compound will always have the oxidation number of -1. And the hydrogen rule says the oxidation number for hydrogen will be +1, with the exception of hydrides, where we see the H- ion. In this example, it's easy to figure out we're dealing with a hydride since we use the group 1 rule first. If sodium is +1, then hydrogen must be -1. In all hydrides, the oxidation number for the hydrogen is -1. Next is the oxygen rule, which says generally oxygen in compounds will have an oxidation number of -2, except in peroxides where we see an oxidation state of -1. And the C in 1,2,3 FHOC isn't for carbon, it's for chlorine. In compounds, chlorine will have an oxidation state of -1 unless it's bonded to fluorine or oxygen. If you remember these rules, you should be able to figure out unknown oxidation numbers in unfamiliar compounds. Just beware that these rules don't work in all cases. Sometimes we need to do high-level calculations. However, these rules will apply in most circumstances. You're most likely to need to work out oxidation numbers when you're looking at reactions. We can analyze the oxidation numbers to work out whether a particular reaction is a redox process or a non-redox process. Here's the reaction of magnesium oxide with hydrochloric acid. We can use the mnemonic 1,2,3 FHOC to remind us which rules we need to observe first. We don't have any group 1 metals here, but we can use the 2 rule to assign the oxidation number for magnesium. Since we're dealing with magnesium compounds, the oxidation number of magnesium will be +2. There aren't any group 3 elements and there's no fluorine. So we can skip those rules and just look at hydrogen. In HCl and H2O, hydrogen is the first element to have its oxidation number assigned. So we can be confident in assigning it the oxidation number of +1. Next, we have the oxygen rule, but in both cases, oxygen is the last element to be assigned in the compound. So we can ignore the oxygen rule and instead work out the oxidation number of oxygen based on the total oxidation number for the compound. In magnesium oxide, oxygen will have an oxidation number of -2 to counteract the +2 oxidation number of magnesium. And in water, oxygen will again have the oxidation number of -2, balancing the 2 +1s of the hydrogens. We need to account for the oxidation numbers of both hydrogens, but we usually only write one above the element symbol. Now we can move on to the chlorine rule. Again, in both compounds where we have chlorine, chlorine is the last element to have its oxidation number assigned. So, in HCl, chlorine must have an oxidation number of -1, and it's the same in magnesium chloride. We need each chlorine to have an oxidation number of -1 to balance the +2 of magnesium. But by convention, we only write -1 once. Now let's see whether any reduction or oxidation has taken place. The oxidation number for magnesium hasn't changed. It's stayed at +2. And there's no change for oxygen, hydrogen, or chlorine. This is therefore a non-redox reaction. Next, we can look at the reaction between elemental calcium and sulfuric acid. We can skip Rule 1 because there are no Group 1 elements and jump to Rule 2 with calcium. But the rules only apply to substances in compounds. Calcium in its elemental form will have an oxidation number of 0. But calcium in calcium sulfate will have an oxidation number of positive 2. Next, we jump to the hydrogen rule. We have H2, which is hydrogen in an elemental form, so the oxidation number of hydrogen here is 0, and in sulfuric acid it's positive 1. Next we have the oxygen rule. In sulfuric acid and calcium sulfate, oxygen is not the last element to have its oxidation number assigned, so we can use the rule. So in both cases, the oxidation number for oxygen is negative 2. We have no more rules left, so we have to figure out the oxidation number for sulfur in the old-fashioned way. The oxidation numbers for sulfuric acid must sum to 0. So we can expand all the oxidation numbers for hydrogen and oxygen. We have an excess of negative 6, so the oxidation state for sulfur must be positive 6. Now the sulfate group in calcium sulfate is identical to that in sulfuric acid. So sulfur in calcium sulfate must also have the oxidation number of positive 6. In this equation we can see calcium going from an oxidation number of 0 to an oxidation number of positive 2. This is an oxidation. And we can also see that hydrogen is reduced, going from an oxidation number of positive 1 to 0. So we've demonstrated we're dealing with a redox reaction. There's also a special type of redox reaction called a disproportionation. In a disproportionation reaction, we see a single substance undergo reduction and oxidation simultaneously. When hydrogen peroxide degrades, one of the oxygens goes from an oxidation state of negative 1 to an oxidation state of 0, so it's oxidized, while the other one is reduced, going from an oxidation state of negative 1 to an oxidation state of negative 2. Reduction and oxidation are occurring simultaneously to the same chemical. Now let's finish up with the key points. We can think of oxidation number simply as an accounting number equivalent to the charge of an atom or ion in a 100% ionic system. There are simple rules we can follow for compounds to figure out oxidation numbers. Group 1, Group 2 and Group 3 elements in compounds will have oxidation numbers of positive 1, positive 2 and positive 3 respectively. Fluorine will have an oxidation state of negative 1. Hydrogen will have an oxidation number of positive 1, except in hydrides where it will be negative 1. Oxygen will have an oxidation number of negative 2, except in peroxides where it will be negative 1. And chlorine will have an oxidation state of negative 1 unless it's bonded to fluorine or oxygen. And elements in their pure forms will have oxidation states of 0.